Hello everyone. Welcome back to my YouTube channel, Chemical Adda. In today's video, we're going to explore a very important topic in chemical process control, the cascade control system. By the end of this video, you'll understand. What is a cascade control system? Why do we need cascade control? What are its components, characteristics, and design guidelines? And of course, what are its real-life advantages and applications? But before we begin, if you haven't watched our earlier video on basic feedback control systems, check the link in the description below. It will help you to understand today's topic better. Alright, let's begin. So first, let's understand what is cascade control system? So, cascade control is an advanced process control strategy used to improve the performance of control systems by using two or more controllers arranged in a hierarchical loop structure, especially in systems with disturbances and time delays. So basically, cascade control is an advanced feedback control strategy that uses two controllers instead of one, such that these two controllers are arranged in a hierarchy. One is called the primary or master controller, and the other is called the secondary or slave controller. And each controller controls a different variable. So, the primary controller controls the main process variable. In example of ACSTR with a jacketed kettle, the main process variable is the temperature of the reactor, T. Similarly, the secondary controller controls a supporting or faster changing variable, like coolant temperature, TC. And therefore, this system gives faster and more accurate control by catching disturbances earlier. Now, let's see, why do we need cascade control? So, let's understand with an example of a continuous stirred tank reactor CSTR with a cooling jacket where an exothermic reaction is happening. So, our main control objective is to keep the reacting mixture temperature, T, constant at a desired value. To do this, we control the coolant flow rate, FC. But, there are two disturbances in this system. Change in feed temperature, which is represented by Ti or Tf. And a change in coolant temperature, which is represented by Tc. And we have only one manipulated variable, coolant flow rate, FC. Now, first let's understand how a single loop feedback control system controls the system if these two disturbances happen. So, if we use only a single loop feedback control system, we measure T and adjust FC directly. So in a single loop feedback control system, firstly, temperature transmitter TT measures reaction mixture temperature T. Then this value is sent to the controller, TC. And then the controller compares this temperature with the set point. Then after comparing T with set point, it adjusts the coolant valve to control the flow rate FC and maintain the jacket temperature. Hence, a single loop feedback control system works well when the temperature TF changes because it affects T immediately and the controller can act quickly. But if coolant temperature TC changes, the effect on T comes after a delay because it takes time for heat transfer and thermal resistance. So, the controller reacts late, after the disturbance has already impacted the process. Which means that, the single loop feedback control system reacts more quickly to changes in feed temperature than to changes in coolant temperature. And, this is the main limitation of a single loop system. That's why we need a better strategy, and that's where cascade control helps. Because in a cascade control system, we add a secondary loop that monitors coolant temperature TC directly, so disturbances are corrected before they affect T. But how? So, let's understand this in detail. But before that, first let's see the components of cascade control. Let's break down the components using our CSTR example. So, a cascade control system has two loops. First one is primary or master loop. In this example of CSTR, the measured variable is reactor temperature T. The measuring instrument is a temperature transmitter, TT. The primary controller is temperature controller, TC. And the output of the primary loop is, it sends the set point to the secondary controller. Then the second loop is the secondary or slave loop. In this example, the measured variable of the secondary loop is coolant temperature TC. The measuring instrument is a temperature transmitter TT. Secondary controller is a temperature controller TC. And the output of the secondary loop is to adjust coolant flow FC via the control valve. So, one manipulated variable FC is shared between two loops, but we use two different sensors. Now, let's see how a cascade control system works. Or we can say, how a cascade control system can solve the problems that we face with a single loop feedback control system. So, we already know that the cascade control is used to improve the performance of a regular single loop feedback control system, especially when there are disturbances that affect the process indirectly. Hence, in a normal feedback loop, we control the reactor temperature T by adjusting the coolant flow rate FC using just one controller. But here's the problem. If the coolant temperature Tc changes, the controller won't react until the reactor temperature T starts to change, and by that time, the process may already be affected. Hence, in cascade control, we add a second control loop that measures the coolant temperature. Now let's understand how cascade control works step by step, starting with the primary loop, then the secondary loop, and finally how they work together. So, in the primary loop, the main goal is to maintain the reactor temperature T at the desired set point. So firstly, a temperature transmitter TT measures the reactor temperature T. Then, this measured value is sent to the primary temperature controller TC. Then, the primary controller compares the actual T with the desired set point T. But, instead of directly opening or closing the coolant valve, the primary controller sends a set point to the secondary controller. So, the primary controller doesn't operate the valve directly. Its main job is just to keep the reactor temperature T stable by giving instructions to the secondary loop. Now let's move to the secondary loop, which controls the coolant temperature Tc inside the reactor jacket. So, firstly, the temperature transmitter TT measures the coolant temperature Tc. Then, this value goes to the secondary temperature controller TC. Then, the secondary controller compares the measured Tc with the set point which it received from the primary controller. And then based on this comparison, it adjusts the coolant valve to change the coolant flow rate FC. And because of this, if anything goes wrong with the coolant temperature, the secondary loop reacts immediately, even before it affects the reactor temperature T. Now, let's look at two possible cases. Case 1, if coolant temperature, Tc, increases. This means that the coolant entering the jacket is hotter than normal. As a result, it removes less heat from the reactor, which could cause the reactor temperature to rise. But, the secondary controller detects this early and increases the coolant flow rate, FC. This extra flow brings down Tc and prevents the reactor temperature from increasing. Then let's see case 2, if coolant temperature, Tc, decreases. This means that, if the coolant is colder than usual, so, it removes more heat than needed, causing overcooling. So the secondary controller reduces FC, allowing Tc to rise back to normal, and preventing T from dropping too much. So, in this way cascade control system works, and reduces the effect of external disturbances, before they reach the main variable. Now let's see, what are the key characteristics of cascade control. First characteristics is, two feedback controllers are used, primary and secondary, to improve accuracy and stability. Then next is, master loop controls the main variable. The next characteristic is that the slave loop controls a supporting variable to help the master loop work better. Next is, faster disturbance rejection. So, the secondary loop reacts quickly to changes and fixes problems before they affect the reactor. The next characteristic is, only one final control element is used. Hence, even though there's only one valve, using two sensors and controllers makes the system much smarter and more responsive. Now let's see, what are the design guidelines of a cascade control system? So the first design guideline is, PID or PI controller should be used in the primary loop to maintain accurate reactor temperature. Next is, P or PI controller should be used in the secondary loop for quicker and more stable response. Then next is, first, tune the secondary loop so it responds fast and correctly, and then tune the primary loop to work smoothly with the already tuned inner loop. Then next design guideline is the secondary loop should react 4 to 10 times faster than the primary loop for effective disturbance handling. Then next is, the secondary variable must be easy to measure and control for cascade control to work well. Then next, let's see what are the advantages of a cascade control system. So the advantages are faster disturbance correction, improves stability and control accuracy, helps in processes with time delays, and reduces the effect of external disturbances before they reach the main variable. Now, let's see what are the industrial applications of a cascade control system. So, the first application, which has already been studied in this video, is how a cascade control system works in reactors, like CSTR. Next application is that cascade control system can be used in heat exchangers. So, here the primary loop controls the outlet temperature of the process fluid and the secondary loop adjusts steam or cooling water flow to handle changes in heat demand. Hence, with the help of a cascade control system, we can easily compensate for the flow rate changes. Next application is in furnaces and boilers. Here, the primary loop keeps flue gas or product temperature at the desired level, and secondary loop which regulates fuel or airflow to respond quickly to load changes. Hence, in furnaces, a cascade control system helps to ensure fuel supply stability. The next application is in the distillation columns. Here, primary loop maintains the desired product composition or tray temperature, and secondary loop controls steam or reflux flow to handle disturbances quickly. Hence, in a distillation column, a cascade control system is used to regulate the concentration. Alright, that's all about cascade control system for today. But before we go, let's quickly revise the key points of today's topic. Cascade control uses two feedback loops, primary and secondary. The primary loop controls the final product variable. The secondary loop deals with fast disturbances. Only one actuator is used, like a valve, with multiple sensors. It's highly effective in systems with time lags, like chemical reactors or heat exchangers. So remember, if your system has delays or is affected by multiple disturbances, cascade control might be the best option. So, if you found this video helpful, please like this video and share it with your classmate. And more importantly, please subscribe to my YouTube channel Chemical Adda. Don't forget to hit the bell icon so you never miss an update. In the next video, we'll cover ratio control and feed-forward control. Stay tuned. And remember, the link to our previous video on feedback control is in the description below. Thanks for watching.